My name is Alejandra Martinez. I'm from Universidad Nacional de Luján, Argentina. And first of all, I would like to thank the organizers for the opportunity to present this joint work in progress in collaboration with Professor Graciela Boente from Universidad de Buenos Aires and CONICET, Argentina. In this talk, I'm going to talk about M-estimators based on B-splines for partially linear additive models. Let's first recall what is a partial linear model. Let yi, zi, and xi be independent and identically distributed observations such that the yi's are in R, zi are in Rq, and xi are in Rd. And they satisfy the semi-parametric regression model where the response variable yi is modeled as a multivariate function m of the covariates plus errors. And this function m is of the form beta transposed zi plus a multivariate function g at xi. Then the objects to be estimated are the vector beta and the multivariate function g. The errors are also considered independent and independent from the covariates. But the estimation of g under this model needs multivariate smoothing techniques, so it suffers from the curse of dimensionality, which is associated to the fact that as the dimension increases, neighborhoods of a point become more sparse. In order to solve this problem, partially linear additive models were proposed. Under these models, the multivariate function g is assumed to be a constant mu plus a sum of univariate functions gj at xj. Then the objects to be estimated are the univariate functions gj and the coefficients mu and vector beta. But are the components of the model identifiable? The answer is no unless we add side conditions. The most common conditions consist of assuming that the expectation of gj at xj is 0. So under these models, we are going to propose M-estimators based on B-splines. But what is a spline? It's a piecewise differentiable curve. Each piece of the function is delimited by points called nodes or breakpoints. Within each interval, the function behaves as a polynomial function with some fixed degree. A fundamental theorem states that any spline function of some degree, smoothness, and domain partition can be written as a linear combination of polynomial functions of the same degree and smoothness, but only supported intervals of nodes with minimal support. And these functions are called B-splines. The number of internal nodes, n, plus the degree of the spline plus 1 is equal to the number of terms, k, of the linear combination of B-splines. Let's see some examples of B-splines. Consider the interval 0, 1 and 0 internal nodes, that is n is equal to 0. Then the number of elements on the B-spline basis is d plus 1. So when d is equal to 0, we have just one B-spline function. But when d is equal to 1, we have two B-spline functions, and so on. When we add also one internal node at 0.5, we have d plus 2 elements in the base, in the B-spline basis. That's why when d is equal to 0, we have two B-spline functions. When d is equal to 1, we have three B-spline functions, and so on. When this equals to 3, the B-splines are also called cubic splines. So the intuitive idea consists of considering a spline basis for each additive function gj in order to reduce the problem to estimate only the coefficients of a linear regression model. So we are going to approximate gj by a B-spline curve in the following way, where bs are the known B-spline functions, lambda s are the unknown coefficients, and kj is the number of terms in the basis, or the number of terms in the sum. So our proposal consists of, with the number of terms in the sum fixed, to approximate gj by a linear combination of B-splines. So by doing this, Now, the response variable, yi, can be approximated by a linear regression model with covariates uppercase gamma I. Then the objects to be estimated are the constant mu and the lowercase gamma, which is a vector. So we're going to estimate mu and gamma using a robust M-regression estimator based on this new sample. More precisely, mu hat and gamma hat are obtained by minimizing the objective function Ln defined in this way, where sigma hat is a robust scale estimator of the standard deviation sigma of the errors, and rho is a raw function. This raw function combined with a robust scale estimator allow us to downweight large residuals and so to obtain more resistant estimators. So the estimators of the additive components are defined in this way, and the estimator of the multivariate regression function is of this form. With respect to the asymptotic properties and the regularity conditions that include sigma hat to be a strong consistent estimator of sigma, we proved that the differences between the truths and the estimators tend to zero almost surely. Besides, we defined an M-scale estimator sigma hat that under mild conditions is a strong consistent estimator of sigma, satisfying the previous assumption. For the selection of the number of elements of the basis, that is K1 to KD, we proposed a generalization of the BIC criteria. When the raw function involved in this formula is taken equal to the square function and this equal to 1, this criteria reduces to the BIC criteria proposed by He et al. 2002. With a real data example, we want to compare the performance of the robust proposal with its classical counterpart. We considered 111 measurements of ozone in New York between May and September 1973, corresponding to the air quality dataset available in R. Here, the ozone is modeled as a partially linear additive model, with its linear part corresponding to the categorical variable month, and 3 additive components corresponding to temperature, wind speed, and solar radiance. In order to compute the robust estimator and the generalized BIC criteria for selecting the number of terms in the basis of B-splines, we used the Takis B-square loss. And the classical estimator and the BIC criteria used the quadratic function. We also considered cubic splines, that is the degree of each B-spline is equal to 3. And same number of terms in the sum for the approximation of each additive function. After computing the BIC criteria, 5 terms for each additive function and both estimators were selected. These plots show the estimated curves for both classical in red and robust in blue, fits together with the partial residuals obtained by the robust estimation. Even though the shape of the estimated components are similar, some differences in their pattern can be highlighted. In order to explore the presence of potential outliers, we plot the box plot of the residuals obtained with the robust fit. And as you can see, 4 observations were detected as outliers. In black points, we can see the partial residuals corresponding to these 4 observations. To study the influence of these observations on the classical fit, we recompute the classical estimation without these 4 observations, and we obtained the following results. This table contains the estimations of the parameters mu and vector beta. The first 2 columns correspond to the classical and robust fits using the complete dataset, that is with 111 observations. But the third column corresponds to the new estimated parameters by the classical fit without these 4 observations. Besides, the plots contain the robust fit and its partial residuals as before. And in red lines, the new estimated curves with the classical fit, but without these four observations. And it can be appreciated that not only the curves are very similar, that's why they are very difficult to distinguish one from another, but also the estimated parameters are very similar too. So we defined a family of robust estimators based on B-splines for partially linear additive models. We showed the estimators are consistent. We proposed a generalization of the BIC criteria. And with a real data example, we showed the advantages in using a robust procedure to estimate the parameters and functions in the model. Thanks for your attention.